Welcome to the year 2050. At a floating ocean port on the equator, humanity is anchoring a structure that stretches directly into the sky. This is the space elevator. It relies on a continuous carbon nanotube cable extending 96,000 kilometers outward, held taut by a massive 12,500-ton counterweight spinning in deep space. To travel up this cable, passengers board the V-pod. It's a vertically oriented, rocket-like vehicle with inward folded wings, designed to firmly grip a tether thinner than a sheet of paper. But that ultra-thin cable is under immense stress, holding 1.25 billion joules of stored elastic energy per cubic meter. If a single fiber breaks without mitigation, the massive tension drops instantly. This triggers a failure cascade, firing detensioning waves and cable shrapnel straight down the line at over 1,000 meters per second. Riding this elevator means enduring a 96,000-kilometer gauntlet against the most brutal kinetic and atmospheric forces Earth can throw at a structure. The first major hazard begins the moment the V-pod leaves the Earthport. For the first 60 kilometers of altitude, the exposed cable and the climbing vehicle are battered by intense atmospheric winds. To prevent the tether from catching that wind and swaying violently, the lower portion of the cable is restricted to a square cross-section measuring just 2.09 millimeters wide. Even with a perfectly aerodynamic track, climbing against Earth's gravity requires an enormous amount of power. If the 100-ton V-pod carried its own chemical fuel, it would be too heavy to actually lift off. The engineers solve this weight problem using microwave power beaming. Ground arrays fire a highly directional, concentrated electromagnetic beam straight up into the vehicle's receivers, supplying energy remotely. This system requires a precise balancing act. The power density must be high enough to push the massive vehicle upward, but strictly limited to avoid causing adverse heating effects in the Earth's ionosphere. Escaping the lower atmosphere means removing the power source from the vehicle itself and turning the Earthport into a remote engine. Once the climber breaches the upper atmosphere, it encounters corrosive atomic oxygen and the invisible threat of the Van Allen radiation belts. These belts are packed with high-energy protons and electrons trapped by Earth's magnetic field. An unshielded passenger passing through the inner belt would absorb a fatal dose of 465 millisieverts per hour. This vector plot shows the V-pod's defense system. Instead of heavy lead armor, it projects a rotating magnetic field. The arrows map electron flow velocity, creating a dual vortex structure that traps high-energy particles, forming a safe biological pocket in the center. Surviving this high-radiation kill zone relies entirely on this active electromagnetic barrier to keep the vehicle light enough to continue the ascent. At 120 kilometers up, the environment changes again. The V-pod enters an orbital debris field heavily populated by micrometeorites traveling at hypervelocity speeds. To survive incoming strikes, the tether morphs from a 2-millimeter square into a broad, curved ribbon. A standard rope would snap from a direct debris strike, but with this wide, curved cross-section, a micrometeorite simply punches 2 tiny holes, leaving the ribbon intact. In the violent kinetic environment of low Earth orbit, engineers secure the cable's longevity by planning for controlled damage rather than trying to deflect every piece of space rock. Pushing past the debris field, the V-pod arrives at the geostationary station, 36,000 kilometers above Earth. The stability of this massive station and entire cable is maintained by pure equilibrium. The 12,500-ton counterweight spins far out in deep space, so its outward centrifugal force balances against Earth's gravitational pull, smoothing out sinusoidal waves rippling along the tether. Scaling this 96,000-kilometer vertical track demonstrates our capacity to combine beamed mobility with active plasma shielding. These exact same tether mechanics and magnetic defense systems can now be adapted for extreme environments elsewhere in the solar system, like the frozen orbit of Uranus or the diamond hail atmosphere of Neptune. By accounting for every lethal variable, we've turned this 96,000-kilometer gauntlet into a reliable anchor for our expansion into the solar system.